Why didn't Jupiter become a star? Was it simply because it didn't gather enough material? And what if, back then, Jupiter had swallowed Saturn too? Would we be living under two suns in our sky? It might sound like pure imagination, but just last month, NASA dropped a shocking update. The Juno spacecraft, a mission that should have already ended, somehow survived and completed its 81st deadly flyby of Jupiter. So what did it see? Today, we step into Juno's perspective, diving straight into the heart of this failed star to uncover the secrets hidden beneath its violent disguise. For a long time, our understanding of Jupiter was surprisingly shallow. We knew it was massive, so big that more than 1,300 Earths could fit inside it. We knew it was a gas giant, wrapped in colorful storm bands, with a colossal, raging eye, the Great Red Spot. But beneath that beautiful surface, what truly lies inside? How was Jupiter really born? To answer these questions, NASA launched the Juno mission, a spacecraft designed to peel back the layers of mystery and reveal what this giant world has been hiding all along. At first, this spacecraft was never meant to be extraordinary. The Juno spacecraft was designed as a routine science mission. Scientists even expected it to fail within just a few months, but something unexpected happened. Against all odds, Juno survived and kept going. Orbit after orbit, it sent data back to Earth. Data so powerful, it hit like a series of shockwaves. The discoveries didn't just challenge what we knew about Jupiter, they shattered it. In fact, Juno's findings went even further, forcing scientists to rethink the very foundation of how planets across the entire solar system are formed. And here's the surprising part. In the history of space exploration, Juno wasn't even considered a flagship mission. Its budget was relatively modest, but physically, it was enormous. With a diameter of nearly 20 meters, it stood out like a giant in deep space. Why build it so large? Because unlike earlier deep space probes powered by nuclear batteries, Juno relied entirely on sunlight, and that's a huge problem. Out near Jupiter, the sunlight is incredibly weak, only about 4% of what we receive on Earth. So to survive, Juno had to deploy 3 massive solar panels, stretching wide to capture every possible ray of light. And even then, the total power it could generate was just over 400 watts, barely enough to explore a giant world full of mysteries. That's barely enough power to light a few old-style light bulbs. In 2011, the Juno spacecraft launched aboard a rocket and left Earth, but it didn't head straight to Jupiter. Instead, it traveled outward for a while, then suddenly turned back toward Earth. At first glance, it looked like a mistake, like wasted time. But in reality, it was a brilliant physics maneuver, the gravitational slingshot. As Juno flew back toward Earth, our planet's gravity grabbed it and flung it forward like a stone from a giant sling. In that moment, Juno's speed jumped by more than 14,000 kilometers per hour. This technique saved enormous amounts of fuel, something absolutely critical for deep space missions. After 5 long and silent years in space, crossing nearly 2.8 billion kilometers, Juno finally arrived at Jupiter in 2016. But the real nightmare was only beginning. To truly see beneath Jupiter's cloud tops, the spacecraft had to get dangerously close, and Juno's orbit was designed in a way that can only be described as extreme. A path that repeatedly dives toward the giant planet and barely escapes each time. One mistake and it would be gone forever. At its closest approach, Juno came within just 4,200 kilometers of the cloud tops of Jupiter. In cosmic terms, that's like flying right up to the planet's face. But getting that close created a deadly problem. Jupiter has the most intense radiation belts in the entire solar system. Any normal electronic system placed inside them would be destroyed within minutes. Even the famous Galileo spacecraft suffered severe damage while passing through Jupiter's radiation, struggling to survive its mission. So before launch, engineers at NASA had very low expectations for Juno's lifespan. To protect it, they wrapped the spacecraft in a thick titanium radiation shield, about 1 centimeter of solid armor. It was basically a tank built for space. At best, they thought Juno might survive a year or two in orbit. Some instruments could fail within months, but then something unexpected happened. As Juno entered orbit, scientists discovered a hidden advantage, a narrow, safe corridor between Jupiter's deadly radiation belts and the planet itself, a kind of natural gap in the danger zone, and Juno slipped right into it, surviving where it was never expected to last. A gap actually existed there, and Juno slipped through it like threading a needle through a storm. It wasn't completely safe. Radiation was still present, but the exposure turned out to be 10 times lower than expected. That unlikely coincidence didn't just save the spacecraft, it opened the door to a scientific revolution, because flying that close meant Juno could finally see Jupiter up close. The Juno spacecraft began sending back ultra-high-resolution images of the poles of Jupiter, and when those images arrived on Earth, scientists were stunned. If you didn't already know it was Jupiter, you simply wouldn't recognize it. The Jupiter we usually see, smooth, banded, almost calm, was gone. At the poles, those neat horizontal stripes completely disappeared. Instead, there was chaos. Dozens of massive cyclones, like endless vortexes carved into the atmosphere. At the South Pole, 5 giant storm eyes. At the North Pole, 8 more, packed tightly together, forming a violent, swirling structure of pure atmospheric chaos, a kind of beauty shaped by destruction. And that wasn't all. Juno also carried a specialized microwave instrument, designed to look beneath the clouds of Jupiter itself. Its job was to see through Jupiter's clouds and look directly into its interior. What the Juno spacecraft revealed next changed everything. Beneath the equator of Jupiter, scientists expected a smooth, well-mixed atmosphere, just vast layers of gas blending together. But the microwave scans told a very different story. Hidden beneath the clouds was a massive, invisible structure, a deep column of ammonia-rich gas stretching downward for at least 350 kilometers. This meant that beneath Jupiter's calm-looking surface, there is an incredibly complex and chaotic atmospheric system, far from uniform. But that was only the beginning, because what truly shook the scientific world was Jupiter's core. For decades, scientists had argued over how Jupiter formed. One side supported the gas collapse theory, that Jupiter formed directly from collapsing hydrogen and helium, like a giant cloud compressing under gravity. If that was true, Jupiter might have no solid core at all, just dense layers of gas. But another group strongly disagreed. They believed in the core accretion model, a solid core forming first, then gradually attracting gas over millions of years. 2 theories, one giant planet, and no clear answer until Juno began to look deeper. They believed that in the early solar system, a massive solid core had to form first, a rocky and metallic interior several times larger than Earth. Only after this dense core reached enough gravity would it begin to rapidly pull in surrounding hydrogen and helium gas. Layer by layer, it would build the thick gaseous envelope we now call Jupiter. And this disagreement lasted for decades. 2 competing theories, no agreement, no definitive proof, because earlier missions didn't have enough precision to see deep enough into Jupiter's structure. But the Juno spacecraft changed that. One of its key missions was to map Jupiter's gravity field with unprecedented accuracy. And gravity is like an X-ray of a planet's interior. If Jupiter were a perfectly uniform solid sphere, its gravity field would be smooth and consistent. But if its internal mass is uneven, the gravity field becomes slightly distorted, subtle variations, almost impossible to detect. As Juno flew extremely close to Jupiter, these tiny gravitational changes began to affect its motion. The spacecraft's speed shifted by as little as 0.01 millimeters per second in response to Jupiter's invisible internal structure. And from those barely measurable changes, scientists began to read the hidden inside of a planet for the very first time. By tracking those tiny changes in speed, scientists were able to reconstruct a detailed map of Jupiter's internal mass distribution. And what came out of the data stunned everyone. Both competing theories were wrong. Yes, there is a core inside Jupiter, but it is nothing like a solid rock sphere. Instead, it is diffuse, blurred, unstable, not a hard stone center, but more like a drop of ink falling into water, slowly spreading, dissolving into its surroundings. The center does contain heavy elements, but they are not packed into a single compact core. They are mixed with hydrogen and helium, blending together in a way that removes any clear boundary. There is no sharp edge, no solid separation, and even more shocking, this fuzzy core is enormous. It may extend to nearly half of Jupiter's radius. The discovery left the scientific community in disbelief, because if Jupiter's interior is truly this chaotic, this mixed, then existing models of planet formation start to fall apart. Without a solid core, how did Jupiter ever gather enough gas to become this massive? The question broke the theory, and to rescue it, some researchers began proposing something far more radical. Maybe Jupiter did once have a solid core, but shortly after its birth, something catastrophic happened. An ancient, massive protoplanet, moving with unimaginable zal, slammed straight into the young Jupiter. A collision so violent, It shattered Jupiter's original solid core into pieces. Those fragments mixed with the surrounding gas, creating the blurred, diluted core we see today. At first, it sounded like the perfect explanation, so scientists turned to powerful simulations using supercomputers to recreate the impact. They tested everything: angles, speeds, planetary sizes, but something strange kept happening. Every single simulation failed. No matter how violent the collision was, over billions of years, gravity would pull the heavy elements back together. The debris would sink, settle, and eventually reform a dense, solid core again, which means Jupiter should not still look like this today. Its core should have rebuilt itself long ago. The mystery only deepened, and just when scientists were running out of answers, a new clue emerged, not from Jupiter, but from Saturn. Saturn's rings are more than just beautiful. They act like a giant seismograph, recording vibrations from deep inside the planet. By analyzing those subtle wave patterns, scientists studying Saturn uncovered something shocking. Saturn's core is also fuzzy, and that changes everything. Because if both Saturn and Jupiter have diffuse, blurred cores, then this can't be explained by a single random collision. It suggests something far more profound. A fuzzy core might actually be the natural state for gas giant planets, which means the standard model of planetary formation, taught for over half a century, could be fundamentally wrong. Data from the Juno spacecraft didn't just answer questions, it reset them. Humanity may need an entirely new theory to explain how these giants were truly born, but that's not all Juno revealed. It also uncovered another terrifying secret of Jupiter: its magnetic field. Jupiter possesses the most powerful magnetic field in the entire solar system, so large that if human eyes could see it in the night sky, it would appear several times bigger than the full moon. And it doesn't just surround the planet, it stretches far into space, reaching all the way toward the orbit of Saturn, spanning nearly 1 billion kilometers, a colossal, invisible force, shaping everything around it. So where does such a colossal magnetic field come from? Deep beneath the surface of Jupiter, around 20,000 to 60,000 kilometers down, the pressure becomes unimaginable, millions of times greater than what we feel on Earth. Under that extreme pressure, hydrogen, normally a gas, is crushed into a liquid state. But it doesn't stop there. The electrons are squeezed free, turning this liquid into something extraordinary: a conductive, flowing substance known as liquid metallic hydrogen. Now imagine this. Jupiter spins incredibly fast, completing one full rotation in just 10 hours. That means this vast ocean of metallic hydrogen, far larger than Earth itself, is constantly churning and moving, like a gigantic generator, the largest in the entire solar system, and it produces a magnetic field of terrifying power. But the Juno spacecraft discovered something even stranger. Jupiter's magnetic field isn't symmetrical. Unlike Earth's neat, balanced field, Jupiter's is chaotic. The northern hemisphere is far stronger than the southern one, and near the equator, there's a highly concentrated magnetic region, a mysterious anomaly scientists call the Great Blue Spot. Even more puzzling, this region isn't stable. It's slowly changing over time, as if the planet's magnetic heart itself is shifting, a dynamic, living force, still hiding secrets we don't fully understand. For the first time in history, humanity witnessed something like this within our solar system. All signs point to one conclusion: the fluid motion inside Jupiter is far more complex and chaotic than we ever imagined. And with that immense magnetic field comes something breathtaking: Jupiter's polar auroras. On Earth, auroras come and go. They flicker, fade, disappear. But on Jupiter, they never stop. It's a permanent light show, a storm of energy that never sleeps. These auroras are hundreds of times more powerful than those on Earth. Through ultraviolet and infrared eyes, the Juno spacecraft captured their true form. And what it saw was strange, because within those glowing auroras, there were mysterious bright spots, not random, not natural, but signatures left behind by Jupiter's own moons, fingerprints of distant worlds etched into light. And that leads to the final chapter of Juno's mission. Originally, NASA planned for Juno to complete just 33 orbits before plunging into Jupiter's atmosphere, a deliberate self-destruction. Why? Because some of Jupiter's moons may hide vast oceans beneath their icy surfaces, places where alien life could potentially exist. To avoid any risk of contamination, to protect those untouched worlds, Juno was never meant to last this long. The safest plan had always been simple: send the Juno spacecraft into Jupiter and let it burn. But in 2021, As the mission neared its end, scientists noticed something surprising. Juno was still in incredible condition. Even after years inside Jupiter's brutal radiation belts, its core instruments were still working perfectly. So instead of ending the mission, NASA made a bold decision: keep going. Not only was the mission extended, Juno was given a new purpose: to explore Jupiter's moons up close. First came Ganymede, the largest moon in the entire solar system. Juno flew just 1,000 kilometers above its surface. The images it sent back were stunning: ancient craters, deep fractures cutting through thick ice. Scientists have long suspected that beneath that frozen crust, there could be a vast liquid ocean. To search for clues of life, the Hubble Space Telescope joined the effort. Studying Ganymede's thin atmosphere, they hoped to find oxygen, but what they found instead was something unexpected. Very little oxygen, but significant amounts of water vapor, a discovery that reshaped our understanding of the moon's atmosphere. Then came the next target: Europa, a world many scientists believe may be the most likely place in the solar system to harbor extraterrestrial life. The Juno spacecraft captured incredibly detailed images of the fractured surface of Europa. Its icy shell is a maze of cracks, twisted, broken, and constantly shifting. In some regions, scientists spotted clear gneiss of surface eruptions. For years, it was believed that a deep ocean beneath the ice was forcing its way upward, cracking the surface open. But new data suggests something even more intriguing. Inside Europa's thick ice shell, which may be around 10 kilometers deep, there could be pockets of high salinity lakes trapped within, like water-filled balloons hidden in ice. From time to time, pressure builds until they burst, sending material erupting toward the surface. To confirm this theory, we'll need future dedicated missions. And then, Juno turned its attention to the most extreme world of all, Io, a place that can only be described as hellish. Io is caught in a relentless gravitational tug-of-war. On one side, the immense pull of Jupiter. On the other, the forces of neighboring moons. Trapped in between, Io is constantly stretched, compressed, and torn apart from the inside. This intense friction generates enormous heat, turning the entire moon into a violently active volcanic world, a surface scarred, broken, and constantly reshaped by fire. The Juno spacecraft didn't just observe Io, it captured it in action. Rivers of molten lava flowing across the surface, and even multiple moments of active volcanic eruptions. Towering stoon of magma, shooting dozens of kilometers into space. But the most shocking moment came in late 2024. During one close flyby, Juno witnessed something never seen before: a massive, synchronized volcanic outbreak. Across more than 60,000 square kilometers, countless volcanoes erupted at the same time, a coordinated fury. This suggests something incredible beneath Io's surface, a vast, interconnected magma network, perhaps even a global ocean of molten rock. And while Juno was watching the moons, it was still uncovering mysteries within Jupiter itself. Years ago, the Voyager program first detected lightning on Jupiter. Scientists assumed it was just like Earth, formed by water vapor deep within warm clouds. But Juno proved otherwise. It captured brilliant flashes of lightning high in Jupiter's atmosphere, where temperatures dropped to -88 degrees Celsius, a place far colder than expected, which means Jupiter's storms don't follow the same rules as Earth. They are stranger, more extreme, and far more mysterious than we ever imagined. At such extreme cold, water should already be frozen solid, so how could lightning even exist there? After careful analysis, scientists arrived at a truly bizarre conclusion. High in the atmosphere of Jupiter, ammonia mixes with water, and ammonia acts like an antifreeze, allowing water to remain liquid even in brutal cold. This creates something extraordinary, a strange, semi-liquid hail made of water and ammonia colliding violently inside the clouds. These alien particles crash, rub, and build up charge until lightning erupts. Scientists even gave them a name: mushballs. Jupiter's weather is no longer just extreme, it's completely beyond human intuition. With every close pass, the Juno spacecraft kept uncovering new secrets, and at the same time, raising even deeper mysteries. Originally, this legendary mission was supposed to end in September 2025. The plan was final. Juno would dive into Jupiter's atmosphere, a controlled destruction, a fiery end to avoid contaminating its moons. But then, something unexpected happened. Because of complex funding and budget issues, NASA never gave the final command. The button was never pressed. And just like that, Juno's story didn't end. In official records, the fate of the Juno spacecraft remains strangely vague, but not long ago, NASA released a report about the ice thickness of Europa, and at the very end, almost casually, they mentioned something astonishing. Juno would perform its 81st flyby on February 25th. Yes, a spacecraft that should have already turned to ashes, that was meant to end its journey inside Jupiter, is still out there, defying its own countdown to destruction, still flying, still exploring, alone in the vast darkness of space. It was sent to solve Jupiter's mysteries, and now its own fate has become one. But at this very moment, it's still alive. And now we can finally return to the ultimate question from the beginning. Why didn't Jupiter become a second sun? The truth is, its composition is almost identical to the sun, mostly hydrogen and helium. It was only one step away from igniting nuclear fusion, but it lacked one crucial thing: mass. And what if it had swallowed Saturn? Well, the laws of physics are far more ruthless than imagination. Saturn may look enormous, but its mass is only about 1/3 of Jupiter. Even if Jupiter had swallowed Saturn, or even every other planet in the solar system, it still wouldn't be enough, not even close. To ignite nuclear fusion and become even the smallest kind of star, Jupiter would need to devour around 70 more versions of itself. That's the brutal reality of physics. So no, Jupiter was never destined to become a second sun. But imagine, just for a moment, if it had gained enough mass, if it had truly ignited, our sky would hold two suns, a world forever changed. But that belongs to another universe. See you there.